So, in case of this do not care condition, so what is happening is that the original function that we are given is incompletely specified function. So, this is an incompletely specified function, because for some of the combinations of input, so we did not mention what is the output. So, the output can be anything. So, the designer is not bothered about the output for those cases. So, in that sense, so I can get multiple functions. So, truly speaking, so if this is the truth table, then suppose for say this particular combination, the output value is do not care. Then it essentially says that I can have two different truth tables. So, in one case, the rest of the row columns, so they get the values from here, but for this particular column, so the value was x. So, I make it 0, rest of the thing remains same as this truth table, and in another case, so I take this one, and for this particular combination, so I take the value as 1. So, essentially this is one function, this is another function. So, this is the original incomplete function f. From there I can derive two completely specified function f 1 and f 2, and we can minimize them and see whichever gives us the minimum result. So, while we are taking these x's in our grouping, so it will automatically take the representation that will have the minimum simplest representation in terms of number of literals and number of terms. So, we can have we can select a function that gives the simplest form, and when constructing the terms in the simplification process, we can choose to either cover or not cover the do not care condition. So, that way we can choose between the alternate functions. So, this is map with some do not care. So, you see that in this case, so these do not cares we have fruitfully exploited to make a quad here. Okay. So, if so that way, so this quad gives me like only b is not changing its polarity, all the other variables they are changing their polarities. So, that is b. Similarly, this quad, so this quad sorry this so this is an octet, so containing 8 ones. So, this is an octet, so that gives me b, and this is a quad. So, that now here a is not changing its polarity and c is not changing its polarity. So, this is AC. So, b plus AC, and this pair, so a is not changing its polarity, and your the a is not changing its polarity, and this c and d, they are not changing their polarity. So, a c bar d is the for this pair. So, accordingly we can do this thing. Another possible covering may be like this. So, somebody does a covering in this fashion. Okay. So, this is one single term, singleton one. So, that is a bar, b bar, c bar, d, like this. Then we have got this a b c bar. So, we take this pair. So, it is a b c bar. Then we have say b c, like say this if I take this term. So, a is changing its polarity, b is not changing. So, b here, and then between these two columns, c is not changing its polarity. So, you get a quad b c, and for this one you get a quad a c. So, this way we can write down a set of quads and singletons and pairs. So, that way we get it like this. So, definitely you can understand that this grouping is not good, because it does not fruitfully exploit the do not cares here. Okay. So, that way the resulting solution is not very good. Next, we look into 5 variable Carnot map. So, so far we have seen up to 4 variable. So, for 5 variable Carnot map, what is done? We take groups of two Carnot maps. One is for a equal to 0, another is for a equal to 1. So, for a equal to 0, so we have got this particular map, or for a equal to 1 we have got a map like this, and then we have this one. So, this is this map is a bar, b bar, d, because for all these terms here a is equal to 0. So, they will come as a bar terms, a bar, b bar, d bar, and this will come as a bar b c. So, this will come as, so a is remaining unchanged. So, a is becoming remaining as a bar. So, between these two columns, E is changing, E is not changing its polarity. So, this term E remains, and between also between these two rows our B is changing its polarity, but C is not changing. So, if you consider only this map, so you get these term, okay, this pair leading to the term A bar, then it is between these from here you are getting say B C, A bar B C, and from here you are will be getting D. So, A bar. So, A bar is definitely there, then this particular row, so it is B C, and between these two columns. So, we have got, so D is not changing its polarity. So, D is coming as, so D is coming as D. So, you are getting B C D, A bar B C D. Now this A bar B C D, so then you can find that from this map. So, this B C D is also there. So, if you take this term, okay, so if you take so if you take, for example, if you take say this single term, so this is your B C D E. Now, this B C D E and this B C D E. So, here also for A equal to 1 map we have got B C D E. So, this from the first map, so I am getting it as A bar B C D E. From the second map I am getting it as A B C D E. So, when they are combined, so this A plus A bar will make it 1. So, ultimately you will get this B C D E. So, in this way, by combining this ones from two different maps, so if the ones are at same position, so you can combine them to make pairs. Okay. So, similarly, say this this term is this pair, this quad is of itself. So, it is A bar B D, A bar B bar D bar. Similarly, so this pair and this pair, so they are located at the same place. Okay. So, they are from the first map. So, you are getting the term as B bar C, and here the D is not changing its sign. So, B bar C D bar. So, A bar in front of that, because it is from the first map, and then from the second for this one. So, for this term, so you are getting the thing like B bar C and D bar and A in front of that. So, if you combine these two, okay, if you combine these two, then this A bars will cancel out. So, you will get the term B bar C D. So, by combining these two pairs, so you can form a quad and you can get the term B bar C D bar. So, this is slightly cumbersome, but it is still we can use it. We can use it for combination across the tables, but it is not that elegant, you can say, but it will be it is useful. Going to 6 variable maps. So, you can so it is so we have got 4 such maps, where A B equal to 0 0 0 1 1 0 and 1 1, they are 4 maps. And again, after making the individual grouping of pairs, quads, etc. So, we have to see whether there exists a similar pair or quad or singleton or octet in the other maps also. So, if it is there, then you can combine them together to get a minimized form. Okay. So, that way you can use this 6 variable map for doing the minimization. So, here you see that these two pairs, so 1 1 here and 1 1 here, so they are at the same place. So, we can combine them. Similarly, say this octet and this octet, so this quad, So, this quad is present in here as well as there. So, you can combine these two quads together. Similarly, this quad is present at in this map and this map, and between these two maps only one variable is changing its polarity. So, you can combine this, but you cannot combine say this quad with this quad, because here A B is 0 0 and here A B is 1 1. So, both the variables are changing their polarities. So, you cannot do this combination, but you can do that as long as they are within the within similar within the quads are the same locations of two maps which are varying only in 1 bit. Okay. So, that way you can do that. sometimes we can do this simplification using some map entered variable. So if you have got more number of variables, you can do that using some map entered variable concept. So this is a situation like I have got a 6 variable map where the terms are expressed like this. So m0 plus m2 plus m3 plus em5, that is if e equal to 1, then m5 will be coming. If e equal to 7, then if e equal to 1, then m7 will come. If f equal to 1, then m9 will come, then m11, m15. So this is represented as 4 variable terms like m0 to m15, but here I have got the other variables introduced, the e, f, etc. So this is actually a 6 variable function, but while writing the function, so we are writing it in we can write it in next less number of variables. So e m5, e m7. So in that map we write it like this. So these don't cares are not written here explicitly, the don't cares are there. So these three are the don't cares that we have. So they are retained as it is, but this e in place of m5 we entered e, in place of f m9, so we enter f, and in place of m7 also we entered e. Now we consider the case where e and f both are equal to 0. If e and f both are equal to 0, so you get a map and we do the grouping like this. So we get a bar b bar plus a c d. Now if e equal to 1, if e equal to 1 and f equal to 0, so we get a map. Now here what we are doing is that we are not considering these ones. So we are taking it as don't care, because this one is already covered by this situation. So this m0 term, so it does not depend on the value of e and f. So we can so that has already been covered here. So they are taken as don't cares. So as soon as some ones are covered, so we can take them as don't cares in the successive formulation. So this is another example. So ABCD is say this one, a bar b bar c plus a bar b c plus a b c bar b c bar d plus ABCD plus some don't care term a b bar c. So this is the, so when we so if you consider d as the map entered variable, so then when d equal to 0, so you put d equal to 0 here, so you will get the function a bar b say, so you get the function a bar c, like if you just take this variable, you take this function and put d equal to 0. So these two terms will cancel out. So you are getting a bar b bar c plus a bar b c. So this b plus b bar will cancel out. So you get a bar c, and when d equal to 1, so we are getting f equal to c plus a bar b. So this is also obtained from this one. Say when you take, so in the map entered variable, so when d equal to 1, so these two terms are coming into picture. The first two term a bar b bar c, so a bar b bar c is coming here. So this is a bar and this is b bar c. So this is 1. Similarly a bar b c, so a bar and b c. So these two are ones. So we have got a b bar c as don't care, that is there. But for the other two terms, so we call them map entered terms. So a bar b c bar d. So when d equal to 1, then this is coming. So this a bar, so this d actually, so a bar b c bar, so that is coming here, and for d equal to 1 it is a b c. So we get the map like this, and then we do a minimization. So first in this map, so we take these two as 1, so because they are always present, so we take them out. So it is independent of so that will give us the term a bar c. So a bar c will definitely come. Then for the second term, so we get this one, it is a map entered variable and d. So these ones are converted to don't cares, because they are already covered by the map where d is not considered at all. So we don't need to do it again. So d is, so for these ones are taken as don't cares here. So you get so now d equal to 1, so you get these two d's as ones. Okay. So now you do a grouping, so you get one term as this one, which is nothing but c. Okay. So that is nothing but c, and from this pair you will get a bar b. So c plus a bar b, and then that is, so this map is coming when d equal to 1, so it is multiplied by d. So then if you expand it, you get a bar c plus c d plus a bar b d. So, this way we can so now if you consider the 4 variable map for the original function, fine. So, this one. So, if you take the 4 variable map, so you see that a bar b bar c. So, it is irrespective of d when it is 0 0, a b is a is 0 and b is 0, then it is independent of this d value, the corresponding bits will be turned on. So, this is the corresponding Carnot map, and here if you do the grouping, you will see that we will be getting back this original term. So, these 3 terms only. So, this 4 variable K map, so we can solve it using a series of 3 variable K maps, using taking help of this map entered variable concept. Though of course, with the increasing number of variables, so this will also become cumbersome, but up to certain length, so up to certain number of variables, so you can try it out. So, another view of K map, so we can view this K map as collection of implicants. So, an implicant, so whenever we are doing this Carnot map covering, so we must cover all ones of the function on the Carnot map. So, you while doing the minimization or writing down the corresponding Boolean expression for a Carnot map, so you cannot say that some of the ones will remain uncovered. Okay, I cannot take the terms such that some of the ones are uncovered. So, each one can be used multiple times in generating the terms of the expression. So, that can happen because one so if you look into a Carnot map, then if this is a Carnot map, and if this particular entry is 1, so it may be covered by several pairs. So, it may be covered like this, also it may be covered like this, it may be covered in a bigger quad or like that. So, that may be that way. So, this particular one may be generated by all the terms. So, here it is covered by 3 terms. So, whenever so this all the 3 terms can generate this particular one. That is why it said that each one can be used multiple times in generating the terms of the expression. Now, when we group ones on a Carnot map, generating a term, that term is called an implicant of the function. So, what is an implicant? So, implicant means that, so it is that term can generate some 1 in the Carnot map, and these implicants maybe we can classify them into prime implicants and essential prime implicants. So, we will see what do they mean. So, a prime implicant is one if you remove any literal from the implicant, then it will result in a product term that is not an implicant of the function. So, in that case P is called a prime implicant. So, implicant means something that generates some 1. Now, if you remove some term, so if it leaves some of the ones uncovered, then it will be called a prime implicant. Like see, these are the implicants, like say suppose this is a Carnot map. So, so with implicant with 2 ones, so these are all the implicants like that. Okay. And if I, so here I have purposefully grouped them into pairs, so that I can all the implicants are covering exactly 2 ones here. Okay. So, these are the implicants. So, these are all implicants. Now, if you take groups of 4, then we will be getting like this. So, these are also implicant because they are covering some of the ones. Okay. But whether they are essential or not, that we will see. So, consider this term a bar b bar d, the first one. Okay. So, a bar b bar d. So, this pair we are talking about. Now, so if we remove a bar, so we get b bar d. So, if I take this b bar d, if I take this b bar d, then what will happen is that so b bar d, so b bar is this row, and so also b bar is this one and this one, and d is this one. And so, b bar d means these ones will also come into picture. So, they are actually not there in the function, fine. So, it says that if you are removing this a bar getting b bar d, so b bar d will cover the original mean terms, like b bar d also covers these 2 ones. So, that way it covers one. So, it can be an implicant. However, on an n variable map, the set of prime implicants corresponds to the set of rectangles made up to 2 power m squares containing ones, with each rectangle containing as many squares as possible. So, a bar b bar d is not a prime implicant. So, because if we remove this, then it will be generating a bigger sized bigger sized quad, in fact you can say, like here it was a pair A bar B bar D. So, if I remove A bar, so I am getting B bar D. So, this corresponds to a quad, like say this means that these two ones and so I am talking about these two ones and these two ones. So, that way, so that will be giving rise to a quad. So, the size increases. So, as the number of literals reduces, the size of the covering increases, okay. Size of the rectangle increases. So, it says that this is not a prime implicant, because if you take it as if you remove this, then some of the implicants are, some of the ones are getting introduced. So, which is not there in the original function. So, this is an implicant, but not a prime implicant. So, A bar B bar D is an implicant, but not a prime implicant. So, if you do this, if you take so it for a prime implicant. So, we should have the set of rectangles made up to 2 power m squares containing ones with each rectangle containing as many squares as possible. So, you cannot maximize it further, that will be called a prime implicant. So, this A bar D, A bar B and B D. So, if you remove any literal from these terms, it will result into an implicant that is not an implicant of the function. Okay. So, they cover all ones of the function and are not contained in some larger implicant. So, these are the prime implicants. So, we will go back to the example and see, like you see that these are implicants. So, these are also implicant, but this particular implicant. So, this A bar B bar D is contained in the larger implicant A bar D. So, this is that A bar D implicant. So, this is covering this lower sized implicant. So, for an implicant to be a prime implicant, it should not be covered by it should not be possible that we cover it by a larger sized implicant. So, that is why this A bar B bar D is not a prime implicant, but A bar D is a prime implicant. So, if you remove any of the literal from A bar D, so it will no more remain an implicant of the function, because some zeros will be now taken as 1. So, that is not correct. However, and also you cannot reduce it, you cannot reduce it further, like this the size of this A bar D cannot be reduced further without undefining the function. But this A bar B bar D, so it is contained in this A bar D in this rectangle, and we have got this this is an implicant. A bar B bar D is an implicant, but is not a prime implicant, but A bar D is also a prime implicant. So, this A bar D, A bar B and B D, so they are prime implicants, because removal of any literal from any of these terms results in an implicant that is not implicant of the function, and they cover all ones of the function and are not contained in some larger implicant. Okay. So, these A bar D, A bar B and B D, so they are covering all ones, but none of the ones are remaining uncovered, and they are not contained in some larger sized implicant. So, these are called prime implicant of the function. So, this way I can say that Carnot map is nothing but a collection of implicants. Out of them are prime implicants, and some of them are essential prime implicant. So, what you have to do is that while after drawing the Carnot map, so the ones that we are putting in the Carnot map, so they are actually the implicants. Now, you have to try to do grouping, so such that you can get some large sized implicants, okay, and then you will land up into a set of prime implicants, and this prime implicants means from there if you cannot remove anything. So, ultimately we are looking for getting the prime implicants. So, two adjacent ones on a map represent a prime implicant, provided they are not contained within a rectangle of 4 or more squares of squares containing ones. Similarly, 4 ones that are an implicant are a prime implicant if they are not covered within a group of 8. So, you can just go back to this example. So, these are all implicants. So, but it is not a prime implicant because it is covered in some larger sized implicant. So, similarly, these 4 ones, so this is forming a quad. So, this is a prime implicant because it is not covered into some sort of octet. So, if for example, if in the original function if these 2 bits were also 1, so these 2 combinations were also 1, then this whole thing would have formed an octet. So, in that case A bar D and so this one and this one. So, they will not remain your prime implicant anymore, but they will be simply implicants. So, that is said here that two adjacent ones on a map, they will represent a prime implicant provided they are not within a rectangle of 4 or more squares containing ones. Similarly, 4 ones that are with that are prime implicant that are implicant. So, that can be a prime implicant only if it is not contained within a group of 8. So, this way it goes on, this prime implicant will go on. Essential prime implicant, a prime implicant that contains a 1 that is not covered by any other prime implicant of the function is an essential prime implicant, and it must be included in any minimal representation of the function. So, these prime implicants, they must be included in any minimal. So, you cannot replace them. So, you cannot avoid them in the minimization process. So, they are called essential prime implicants. So, like in this case we have got prime implicants A bar D, B D bar and A bar B. So, these are all prime implicants. Out of that, say this A bar D and B D bar. So, they are essential prime implicants. So, if you see that while doing this grouping, so this is somebody has done a grouping like this, as well. This grouping. So, from the map itself you can understand that there is some redundancy here, like so for example, the ones have been covered by more than so these two ones. So, they have been covered by this as well as by this. So, similarly, these ones have been covered by sorry. So, these ones have been this one has been covered by this as well as by this. So, it may be possible that we can get rid of some of these groupings, and we can get the we can still get the minimized form. So, that is what is told here, that these are all prime implicants. So, A bar D, B D bar and A bar B, because they are containing ones in them, but they are not essential because you can get rid of some of them. Like, so, it is like if you say this A bar D. So, A bar D is this one. So, A bar D A bar D is so this grouping is A bar D, the first one. Okay, so, this grouping is A bar D. So, if this A bar D and this B D bar, if you take, then so this is B and if you take these two. So, actually this particular grouping. So, this is B D bar. So, if you take these two, it is only, so this all the ones are getting covered, but in that case we do not need this particular grouping of A bar B. So, A bar B is not essential. So, you can take A bar D and B D bar, but if you take say A bar D and this A bar B, if you take A bar D and A bar B, then also it is fine. Okay, so, that may be another possibility. So, that way so this is also not unique. So, I can also take another one like say A bar D and A bar B, because A bar D will give me this one, okay, and A bar B will give me no A bar B, no A bar D, A bar B. So, this is not essential, this will not give me full coverage. So, this is my A bar B. So, these ones will remain uncovered. So, this is these are not, this cannot be taken as essential prime implicant. So, A bar B is not essential. So, we have got A bar D and B D bar as essential prime implicant. So, the minimum form is A bar D plus B D bar. So, essential prime implicants we cannot remove. So, non-essential prime implicant, sometimes if you take this example, you see that if you take only prime implicant, so you will get a grouping like this. Okay. But you see that these ones, it is so this particular this one is covered by more than ones like that. So, that way it is we are taking some non-essential prime implicants. So, include those that are essential. So, if I just so in the previous case, So, this is covering, this is showing all the implicants that I can make. Okay. So, these are all the implicants that I can make. From here I have to choose the essential set. Now, how do we choose the essential set? For we take those that take ones that are essential. So, these are essential. So, I take this thing. So, this was not essential because this is already covered by that. But the problem is that after taking the essential one, so this one is left and this one is left uncovered. So, in that case we have a choice. So, we can take say either this one or that one. So, we have got two choices for covering it, both of equal size. So, we can check either of them and ultimately come to this representation. So, by taking after choosing the essential one, so we have to check check some others which if some ones are still left, and then we can have a choice. So, I can group this one with this one or this one. So, this one can be grouped like this, or so I can group it in this fashion, or I can group it in this fashion. So, both are possible, but in whatever you do ultimately you get the same type of cost. So, that way it is same. So, we want to minimize the overlapping. So, that way we can try to do as much minimization as possible by doing this selecting in such a fashion. So, this is another example. We have got these ones, and then we cover the largest group of ones. So, this is there, and after that we can, after selecting this, select the ones that are not covered yet. So, this is the one that is not yet covered, we select that one. Then we select another group that is not covered yet. So, we have essential, we have essential part we have done. Now, we have got a choice. So, this one may be covered with this or it may be covered with this, both are having equal cost. So, if we take the example that is shown here, so it is giving me this particular expression, whereas if I do a grouping with say this one and this one. Okay. So, these two ones are grouped. So, you will get the second configuration, but both of them are having same number of literals. So, they are just same, they are getting the same. So, that way in Boolean expression minimization, so we can use Carnot map, and we can have different views. It may be viewed from a set theory approach, it may be viewed from the implicants approach. So, whatever you do ultimately it is a matter of covering. So, if you in the covering process, so if you are not taking the redundant ones, then you will definitely get the minimum form with minimum number of literals and minimum number of terms.